Okay, chapter 14. So chapter 14 will be in two parts since I decided it was really long, um, to just go in one part. So 14. Okay. Share screen. Sorry about that. Okay. Chapter 14, let's talk about it. Okay. So first concept we're talking about the heart. Okay, so cardiac output. How much blood is your heart pumping out? And that is determined by two numbers. Okay. The first number obviously is your heart rate, right? How many times is your heart beating? Second one is your stroke volume. How much blood does each pump actually squirt out? Okay. And the two numbers are actually identical, like they're both 70. Okay, so the average heart rate is about 70 beats per minute. Your average stroke volume is 70 to 80 beats milliliters per beat. So your average cardiac output is about 5 liters per minute. Okay, so that's 5.5. So 5 to 5.5 usually. Okay, depending on how fast your heart's beating. Okay. Okay. Factors that affect heart rate or regulation of cardiac rate. Okay, first of all, your regular beating of the heart. Okay, you have the parasympathetic innervation and the sympathetic innervation. Okay, sympathetic innervation increases heart rate. Parasympathetic slows heart rate. Okay. All right. So positive chronotropic effect increases the rate. Negative chronotropic effect decreases the rate. These are the definitions. Okay. So here's the essay node. Okay, so you can see the differences between sympathetic innervation and parasympathetic innervation. I'm going to talk about the atrial muscle and the ventricular muscle in a little bit. Okay. Okay, stroke volume. Okay, the regulation of stroke volume. Okay, regulated by three variables: the end diastolic volume. Okay, also known as preload. How much blood is actually physically in the ventricle before it contracts? Obviously, the more blood is in there, the more you're going to squirt out. Okay. Number two, the total peripheral resistance, the amount of resistance to the pushing of the heart valve or the compression of the ventricle. Okay. So total peripheral resistance is the resistance in the arteries mathematically summed up. Okay, so the frictional resistance in the arteries. So the more resistance, the harder it is for your heart to pump, and the less volume comes out. Okay, so it's easier to pump into empty air than against something that's pressure. Right? Okay. Okay, contractility, the strength of which the ventricles contract. How hard is the muscle squeezing? Okay, normally about 60% of the EDV is ejected, and this number is known as the ejection fraction. Okay. Okay, the Franklin law of the heart, the increased EDV, so more volume results in increased contractility, which so as the ventricle contracts, it's going to squeeze harder to come back. So it's going to end up being increased stroke volume. Okay, due to myocardial stretch, the increased EDV stretches the myocardium, which causes a increase in contraction strength. Okay. All right. So adjustment for rise in peripheral resistance. So increased peripheral resistance will decrease stroke volume. If there's more resistance to it, then less fluid will come out. So the more fluid remains in the ventricle, so EDV increases, and then the ventricle to stretch more so they contract more slowly. So they fight back against the peripheral resistance. Okay. All right, extrinsic control contractility. Contractility means the fiber is able to contract. Okay. 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 So sympathetic innervation, more calcium, more contraction. Okay. Parasympathetic innervation will actually increase EDV as well because there's a slower heart rate, but the slower heart rate will increase EDV, which means there's only more stroke volume per beat. But that still doesn't counter the less number of beats. You get more blood out per beat, but less beats. Okay, so less cardiac output. Okay. Okay. So cardiac output is equal to cardiac rate, so parasympathetic, sympathetic. Okay. The sympathetic also affects stroke volume to increase stroke volume. So you get more, like the sympathetic, you get higher cardiac rate and higher stroke volume. So not only are you pumping faster, you're pumping harder with each pump. Okay. Okay, the end diastolic volume is controlled by two factors, the total blood volume and the venous pressure. Okay, how much pressure there is in the veins tells you how fast the ventricle is filling. Okay. Okay. So veins have high compliance, which means they stretch more so they can accommodate more fluid. Okay. And so you can actually see the veins actually contain most of the fluid and the arteries contain very little of the blood supply actually. So yeah. So but these arteries are under much higher pressure. Okay. So the sympathetic nerve activity stimulates the smooth muscle contraction and lower compliance. Our skeletal muscles also pump in the veins. When we move, they squeeze on the veins and drive the veins up, or drive the fluid in the veins up. Okay. The pressure difference between the abdominal and thoracic cavities when we breathe, okay, also puts pressure on the veins. And lastly, the blood volume. Okay. So here, the pressure, etc. Okay. All right, about 2/3 of our body water is found in the intercellular fluid. That about 80% is in the of the remaining is in the interstitial spaces, and only 20% is in the blood plasma. Okay, osmotic forces control the movement of water between the interstitial fluid and the plasma. Okay, so which affects blood volume. Okay. Okay, so here is your total interstitial volume versus your blood volume. Okay, So per 24 hours, you get rid of 1.5 liters of fluid of urine. You breathe out this much, you sweat out that much. Okay. And then obviously your input, output here. Okay. All right. Okay. So things go from high pressure to low pressure. So hydrostatic pressure on the arterial end is 37, and the venial end is 17. Okay. So what you're going to see, okay, is fluid leak out. Okay, and that's countered by the osmotic pressure here in the blood plasma. Okay, so okay, so basically this is fluid in, was fluid out. At the beginning of the capillary bed, fluid actually comes out. At the end of the capillary bed, fluid actually runs in, and there's net absorption of water. But even with that, there's still fluid that is leaking out right here. Okay, the overall process leaks a little bit of fluid out, and that's really important because that little bit of fluid contains the nutrients and oxygen that we need. Okay, and where it leaks into is the lymphatics. Okay. Okay. So about 10%, okay, remains, and then it leaks into the lymphatics. Okay. Okay. Edema is an excessive accumulation of interstitial fluid, maybe the result of high arterial pressure. Okay. So more pressure on the front end causes more fluid to leak out. Venous obstruction and the leakage of plasma proteins into the interstitial space. Remember, it is the plasma proteins that's driving the fluid to leak back into the capillaries. So if you leak those proteins into the interstitial space, then there's no pressure to drive the fluid back into the capillaries. Okay. Edema, blah, blah, decreased plasma protein concentration. Like I said, that's wash core, and obstruction of lymphatic drainage. Okay. All right. Prepare to be grossed out. This is elephantitis. So you block the venous drainage, and this is what happens. Okay. All right. Regulation of blood volume by kidneys. All right. So the first thing that kidneys actually do is make filtrate. Okay, when you filter blood, the first thing you make is filtrate. You filter 180 liters of fluid a day out of your kidneys. Okay, as a comparative. Obviously, you're not peeing 180 liters out. Okay, most of that gets reabsorbed. Okay. The amount of fluid reabsorbed is controlled by several hormones and the sympathetic nervous system in response to the body's needs. Okay. All right, the role of the sympathetic nervous system. The increased blood volume in the atria, similar stress receptors that lead to sympathetic stimulation, the heart, and decreased stimulation to the kidneys, so less urine being made Okay, the kidney arterial phthalate, which increases the blood flow and increases urine production, that will decrease blood volume. Okay, ADH or vasopressin. ADH and vasopressin is produced by anterior pituitary. Or no, ADH is posterior pituitary. Okay. So when there's too much salt in the blood, increased plasma osmolarity, that tells you there's not enough water, so you release vasopressin. Vasopressin can cause reabsorption of the water in the kidneys, and that increases blood volume. Okay. So increase water intake, decrease urine formation. Okay, stretch receptors in the left atrium. The carotid sinus and the aortic arch inhibit ADH release. These things measure blood volume, and there's too much, and you want to inhibit ADH release. Stretch receptors in the atria also release ANP. ANP is the exact opposite of ADH. It causes increased excretion of salt and therefore water. Okay. So if I move salt, I move water. Okay, so think about it that way. Okay, if I move salt in, I move water in. If I move salt out, I move water out. Okay. Okay. Aldosterone is secreted by the adrenal cortex indirectly when blood volume and pressure are reduced. Okay, which stimulates the reabsorption of salt and water in kidney. Okay, and it's regulated by the angiotensin, renin-angiotensin aldosterone mechanism. Okay, is either called the RAA or the RAS. Okay, renin-angiotensin system. Okay. So when blood pressure is low, the kidneys secrete renin. Renin is converts angiotensin to angiotensin 1. Angiotensin 1 is converted to angiotensin 2 by ACE. Okay, this is the thing COVID-19 is actually binding to. Okay, and then angiotensin 2, okay, works on the adrenal cortex to produce aldosterone, also causes vasoconstriction. Okay. ACE inhibitors, okay, block this, and therefore it causes a decrease in blood pressure and blood volume. Okay, ANP, I already told you, when the atria overfill, they release ANP, and ANP gets your kidneys to pump out salt and water. Okay. Okay. So prolonged exercise can cause the loss of water and electrolytes due to sweating. Okay, the effects of this include lower blood volume, lower cardiac output and blood flow, reduced ability of the body to dissipate heat. Okay, so Gatorade. Okay, so in case you're wondering where Gatorade comes from, Gatorade was actually made by scientists at the University of Florida, Florida Gators, hence Gatorade. And what they developed was a sports drink that increased uptake. The salt So if you actually go try Gatorade, actually you taste the salt a little bit. The salt helps the water, okay, the electrolytes go into the system, and it helps it stay in the system, so you don't lose it. So you have higher blood volume. Higher blood volume allows you to outperform the people with crappy blood volume. Okay, and so Gatorade. Okay. Actually, you know what? I'm gonna stop right here. I'm gonna pick this up in part 2. Okay. So sharing.